My interest is a lot in um, your own work and how you think your work might be used in the future by other researchers. You spoke about the data sets that you used had biases, and you made your own data set. That just sounds amazing to me. So is that something that you think will be used by other researchers, for example, and your platform
Yeah.
in general? Yeah.
So that data set, so everything I presented was in my PhD. So I had four very different research chapters, and I was like, how am I going to mesh these together into a thesis? And the main reason, so I had like a nice flow to my research, and then basically, so when I was using those planform stability fields from Gary Parker, but also there are loads of different planform stability fields. I investigated loads of them. The reason that I settled on Gary Parker's one is because it required the least amount of assumptions. So when you're dealing with the rock record, you want to minimize the amount of assumptions that you have to make, because the more assumptions you make, the more uncertainty you have. So I settled on Gary Parker's one because, not because I was trying to pick on him, but because that one was going to be the best for application to the rock record. And this is basically in, I think it was lockdown one. I basically went down a rabbit hole of there's only 53 data points in this data set. I need more. If I ask my PhD supervisor if I can work on this, he's going to say, no, Sinead, write your thesis. So I waited till he was on annual leave and I just did it. I just started collecting data. And he came back from annual leave and I was like, oh, I have an idea. And he was like, oh, and I just showed him, like, I think by that point, I'd already had 400 data points and you could already see that a load of the multi-thread rivers were on the wrong side of the line. So he was just like, you keep going, you keep doing that. Um, so yeah, kept building it up, set like 1,700 data points. We published it, so people have started to use it, and I hope people continue to use it. I've been adding to the data set. I'm basically trying to source a very computer savvy undergraduate student or graduate student who wants to like code up a little online database so that I can dump all the data there. So I published the data set as an Excel spreadsheet at the time, but I've been adding to it. And in my head, it would be nice if there was like a little online thing where you could go and you could like select the data you want and kind of take that. But yeah, it's nice to see that people are already using that. In terms of the kind of the other work, so it would be nice to, I mean, we're getting so much more data remotely um, from Mars and things like that. And I've seen people start to do landscape reconstructions for Mars. Um, for me, I think the thing that I like the most is I'd say as people have started to kind of make these kind of quantitative reconstructions of fluvial landscapes, it's been very kind of case by case. So we're going to look at one system, going to reconstruct everything, and then someone else will look at another system and reconstruct everything. But I think the major benefit of actually pulling out quantitative constraints is that it enables you to compare different systems. So just from this image that I have on the screen, so here in the Castlegate sandstone, the kind of flow depths were a couple of meters deep, whereas here and the catchment, we're about, I think here we're probably maybe 70 kilometers from the source region. Whereas here in the Willwood Formation, these, to be fair, they're probably also maybe a couple of meters deep, but up to maybe 6 or 7 meters. But we're much further from the source region. So just having these numbers helps us to compare different systems, which systems were larger than others. How did this system respond to change? How did this system respond to change? So I think that's where we're going to start going forwards. And I think that's how we will continue to grow.
Um, and there's a question in the chat from Tony Brook. I don't know, Tony, do you want to ask your question yourself?
Yeah, you basically showed the Western United States system, and if you got flow rates, you can make a fairly good estimate, I'd have thought, of your catchment area. Therefore, you could use that to estimate rainfall over time, couldn't you?
Yes, you have gotten at my active research topic right now. So, um, one thing that I found really interesting is so when we're thinking of climate proxies, so geochemical climate proxies, they tend to be quite robust for if they're marine proxies. So I don't do the geochemistry. The geochemists do the geochemistry, but when the geochemists reconstruct paleo temperatures, they often use marine proxies, and they're getting at like the marine sea surface temperatures, things like that. And they're quite confident about those. However, terrestrial temperature proxies, they're a bit trickier because well, the sea surface temperatures, they kind of give you good insight into what the mean temperature is. Whereas terrestrial proxies, the proxy might be a leaf fossil, or it might be, I don't know, some other kind of plant fossil that they might use. And the problem with terrestrial temperatures is that you have a lot of variation in temperature throughout the year. And you also have a lot of variation in temperature in space. So just with the presence of topography, so like valleys and things like that, temperature varies a lot from one side of a valley to another and at different times of the year. So if you're using leaf fossils to try and reconstruct temperatures, you might just be getting an insight into the temperature of a particular season in a very particular regionally restricted area. So people who've used kind of climate models to try and reconstruct terrestrial temperatures, in general, when people have used climate models to reconstruct past temperatures, they've often found there's really good agreement between model reconstructions of sea surface temperatures and then geochemical proxies of sea surface temperatures. But they found there's a lot of disagreement between model predictions of terrestrial temperatures and then proxy predictions of terrestrial temperatures. So one thing that I've been thinking a lot about is that if you have kind of reconstructions of water discharges from the geologic record, if we made the assumption, you'd have to make a mass balance assumption. So you'd need to do it for like a single thread. You'd want the major trunk channel of a system, but for that kind of, if for a cross section through that channel, if you could estimate the water discharge, you could make an estimate of the catchment averaged precipitation rate. You would also have to make an assumption of the runoff rainfall ratio, but that's potentially going to give you a more spatially averaged proxy of the climate condition, as opposed to an estimate that's very kind of restricted in space and time, if that makes sense.
Yeah. Can I add another thing? I went to a lecture with Dorset about 2 years ago, where the guy was taking all the information from NASA of Mars, and he's like saying, I can show you examples of volcanic mechanisms that generate all of these profiles. And he could not see he couldn't show a single example, which had to be only due to water. And he was reasonably convinced that they're going to find that it's all due to volcanic process.
Oh, wait. Oh no, I can't. I had a picture of the surface of Mars earlier. Very nice meandering point bar deposits. I cannot be convinced that those are volcanic.
So he's been selective, has he?
Yeah, I think
He might
so.
have been selective in what he did, but he showed all of these things and then showed features from Hawaii, where you get very liquid lavas and
Yeah,
yeah.
Oh,
the Pahoi Hoi lavas, they're very kind of ropey and runny, but no, these I can maybe share some nice images with Liz who can share them around
oh,
of
great. Yeah, thank you.
very nice,
Do that.
definitely fluvial things on Mars.
Yeah. Can I just come back to see if Nikki Edwards wanted to ask? Because
Yeah, I was just going to say very humbly that how much evidence have you found of extreme weather conditions at the PETM? We're experiencing more extreme weather now. Is it quite clear that the climate changed dramatically as well?
Yeah, so when people have studied the PETM and they've tried to reconstruct the climate response to the PETM, these have mostly been focused on changes to the mean conditions. So geochemists have predicted that mean temperatures increased by 5 to 8 degrees Celsius and that the mean precipitation increased. But with kind of proxies, it's kind of hard to get at the seasonality. So you could have an increase in the frequency or the magnitude of a discharge event, without changing the mean conditions. So you might just change the shape of the hydrograph, but still end up with the same mean. So that's kind of hard to predict, but they've started to look into that with climate models, and with climate models, they've been able to pull out, okay, so maybe the mean precipitation only changed a little bit, but using a climate model, we can see that the wet season had a much higher precipitation rate, and maybe the dry season had a much lower precipitation rate. So models, they're starting to kind of look into that. From the field, I've been trying to look into that. So again, if we make the assumption that stratigraphy is the product of the biggest events. So normally when we think of rivers, we think of bankful conditions do all of the hard work. So if you have like a nice river, maybe the average flow is like tens of centimeters at the bottom of that channel. However, when you have a really big rainfall event, you might fill the channel to the brim, and those would be the bankful conditions. And if they exceed bankful, you get the flood. And so generally, as a community, we accept that when the channel is filled to the brim, or when it's overflowing and it's in flood, that's when the river is doing most of its work. That's when it's moving the most sediment. That's when it's carving new paths. That's when it's carving new shapes. It's widening, whatever it needs to do. So when we look at the stratigraphic record, we tend to make the assumption that what we see is the product of the biggest events that were happening. So if I go up to stratigraphy and I'm looking at a load of conglomeratic deposits, I'm going to make the assumption that this was done by the largest events. So if you're reconstructing water discharges and things like that for these big events, you could make the guess that maybe what I'm doing is I'm reconstructing flood discharges, and maybe I can see changes in flood discharges through time. But this is something we're only thinking about this now, and this is something that I was literally trying to run some code yesterday to try and get my estimates for the PETM in Spain. So we shall see. But yeah, that's the exact pattern that we're seeing today. So, if I think of the Thames, I'm not going to notice a change if the mean discharge, I think the mean discharge of the Thames is something like 90 meters cube per second. If the mean discharge of the Thames increases to 100 meters cube per second, I'm not going to notice that. But what I will notice is if the frequency of flooding changes, or if the magnitude of flooding changes. Like, those are the things that we notice. So when we're thinking about how rivers respond to change, those are the things that are important to us and we care about. So when we're looking at the past, we're kind of trying to shift towards thinking about the extreme conditions and whether we can get at how those changed.
Okay, watch this space.
Thanks, Joan. Do you want to ask a question?
Yes, just out of interest, is Lidar of any help with your work?
Yes. So my colleague, so one thing that you can do with Lidar and kind of any of these kind of satellite products, anything remote sensing, where you have a good record of that going back, so for example, Landsat imagery goes back many decades. And a graduate student in my research group is basically using remote Landsat imagery among other products. And what she's trying to do is she's trying to take rivers and she's trying to track how they've moved across the last 30, 40 years. So one thing that you can do is if you're looking from satellite and you can trace the center line of a river in each successive imagery, so maybe you have one image per year, in each image, if you trace the center line, you can then figure out how much the center line moves and you can work out how much the channel has migrated. So I did have a GIF earlier of that meandering river on a loop that just kept moving. So you can kind of get at that migration rate. And the reason that would be useful to sedimentologists is because it's that movement of the channel that produces the bar deposit, which ends up in the rock record. So in the rock record, if you have a bar that's very kind of short, that means your channel has migrated so far before either the flow was cut off or the channel moved away or something like that. Whereas if you have a bar deposit that's really, really, really long, that means that your channel migrated a lot further across the floodplain before the flow was cut off or the channel moved away. So yeah, a lot of this kind of remote sensing imagery is, it's only kind of recently become very available and accessible, but everyone is jumping on it